one particular complex. If you look at this complex, the complex part is minus. So if I talk about the IUPAC name, cesium, tetrachlorido, ferret, -4 + 1, 3. This is the complex. This complex coordination number is 4. So coordination number 4, if we consider this one as tetrahedral complex, the splitting of the d orbital is just opposite to that of the octahedral complex, which I have already discussed. So these are the 5 sets of d orbital. Now we know that the dxy, dyz, dzx, the lobes, the double dumbbell is in between the axis, and dz square and dx square minus y square is along the axis. Now in a tetrahedral complex, what happens? There will be 4 ligands, means 4 donation site. If it is bidentate, 2 ligands will be there. The ligands will approach towards the central metal in between the axis, and when it comes in between the axis, dxy, dyz, dzx, these 3 orbital will be repelled much more higher. So they will go up, and the EG set, which is along the axis, they will come down. This gap is called tetrahedral splitting. Now in case of tetrahedral complex, in terms of symmetry, it do not have the Garrett symmetry, so we write T2, and this one we write as E, because tetrahedral complex has no symmetry in terms of Garrett or ungarrett, so that G term will be not there. This iron is in the oxidation state of 3, and since it is in the oxidation state of 3, its electronic configuration will be this one. Now all of us know from the spectrochemical series, chlorine is a weak ligand, so this delta T will be small. So this 5 electron will be filled up singly, Hans will be followed. And if I talk about the electronic configuration, E2, 2 electrons, and this T2, 3, this will be the electronic configuration of this particular complex. So if I talk about the splitting of the d orbital, in a tetrahedral splitting, the splitting is like this, and the octahedral splitting is opposite but bigger. This is your delta octahedral, this is delta T, simply because the approach of the ligand. In octahedral, the ligand come along the axis, T2G, they will go up, and the EG will go up, and the T2G will come down. And in case of tetrahedral, this is the gap, the E, T2 will go up, this is T2, this is E, this is EG, this is T2G. Simply, the G terms will be not there in tetrahedral splitting. And you see this delta O is much more higher than delta T. So tetrahedral splitting and octahedral splitting, if I write 4/9, delta O is delta T. That means delta T is almost half. 4/9 is almost half compared to this one. So this is simply because in case of tetrahedral complex, 4 ligands are approaching central metal. In case of octahedral complex, 6 ligand is approaching. So 6 ligand will create greater gap between the 2 sets of d orbital compared to this one. So that is the reason the octahedral splitting is much more higher than the tetrahedral splitting. Whether it is octahedral, whether it is tetrahedral, the 5 sets of d orbital which is together degenerate is broken into 2 sets. So whenever there is jumping of electron, it will take from one d level to another. In case of tetrahedral, or here, the jumping will be dd transition, so they will be colored. If there is no d electron, color will be not there, because the dd transition falls in the visible range, and whatever absorption will be there, complementary color will be shown. Now color, when you talk about color, 3 reasons are there for color. One is called dd transition. It may be FF transition also. Charge transfer transition, that is called CT. and crystal defect. These are the three causes of color in chemistry. Say for example, zinc oxide, white. Heat in a test tube, it will become yellow. Cool it, it will again become white. This is due to crystal defect, the color is coming. If you talk about potassium permanganate, manganese oxidation state is +7, electronic configuration is 3d0, no d electron is there. How the d transition is taking place? So this should not be color. But potassium permanganate has a color, almost violet color. This is because of the charge transition. Because the permanganate ion, this is the permanganate ion, manganese is in the high oxidation state. The negative charge is transferred towards the positive charge. That is called CT, charge transfer. Potassium dichromate. Chromium is +6, no d electrons, but it is orange in color. This is also because of the charge transition. Chromium +6, oxygen to chromium electron transition takes place. That is called charge transfer, and that falls in the visible range. So these are the basic reasons for color in chemistry. We are concerned with the DD transition in class 12, and DD transition may be tetrahedral, may be octahedral. So whether it is tetrahedral or octahedral, the DD transition always, that gap falls in the visible range. And that visible range is the 7 color we can see. But if you talk about water, it is white. Sodium chloride, white. Why? No color is there. Because these are nothing but SS or PP transition. P orbital to P orbital, SS. And this falls in the UV range. So obviously there will be no color. We look it as white color. Thank you.